For last speaker of the day is Biren, and he will be talking about accelerating infrastructure with DPUs. Biren, can you introduce yourself? Thank you.
Yep, thank you very much. Can you all hear me? Yeah, okay, fantastic. So we live in a world that's powered by data. We are data dependent, and demand for data continues unabated. The current digital infrastructure is not optimized for data-centric compute. Good afternoon, folks. My name is Biren Mehta, and I lead the Network and Edge Infrastructure segment at ARM, and I'm thrilled to be here with you all to discuss how we think about data-centric compute and what it means in terms of DPU and where how it plays a role in that space. But before I get started, let me do a quick introduction on who ARM is and what do we do. We are a semiconductor design house with a global leader in a licensable compute technology. We license a range of compute IPs, from core to interconnect to compute subsystems to system IP. Our customers and silicon partners have shipped to date over 250 billion ARM-based over 250 billion ARM-based powers that sensors and smartphones to cloud giants to power the compute infrastructure. Demand for high performance and sustainable compute is growing exponentially, and we recognize that we don't and we won't accomplish this alone. Hence, we actively collaborate with open ecosystem to build sustainable SoCs, share knowledge, and solve complex problems together. With that introduction, let's have a quick look at the current market dynamics. As you've repeatedly heard this week, the Moore's law is hitting the wall. The single core performance is plateauing, while demand for compute is outpacing supply. Moreover, the SoC design costs are rising as you move up to the next-gen nodes. SoC design costs are nearly $600 million on a 3-nanometer advanced node. Hence, monolithic die with integrated compute, accelerators, and I/O becomes cost prohibitive and opens up the opportunity for chiplets to amortize cost. Further, connectivity and data I/O is increasing rapidly. Just to give you some statistics, there are today 15 billion IoT connections, 1 billion 5G subscribers, and over 120 zettabytes of data generated and growing fast. Just to give a quick math, that's about 120 billion worth of terabyte data. So this ever-increasing data and network I/O is straining the connectivity and compute infrastructure. A traditional scale-up and compute infrastructure is straining the overall infrastructure. So therefore, a scale-up Swiss Army knife approach to computing is ineffective at handling data-centric heavy workload, like networking, security, storage, AI, ML, and what have you. And also, it results in high TDP infrastructure. Second, commingling of this infrastructure and tenant workloads results in host CPU being, basically having a very weak security model, because think about a infrastructure workload and tenant workload all residing on a single host CPU. And so that results in a stranded resources due to siloed architecture. So to address these market realities and infrastructure inefficiencies, we need a scale-out data-centric architecture powered by domain-specific accelerator with right-sized compute complex. Simply scaling up the compute architecture by throwing more cores and accelerators as depicted on the left is not sustainable and leads to inefficiencies in resources such as utilization, stranded resources, weaker security constructs, and siloed architecture. In contrast, On the right, you have an architecture that is scale-out, data-centric, where DPUs are connected in fabric and has a full visibility and control of the entire infrastructure resources, from CPU to storage to memory to GPUs, and that are available fabric-wide. So you can stitch required resources on demand based on the workload needs. So this cloud-like composable infrastructure delivers optimized processing of data-heavy workloads, tighter security with clean separation between tenant and infrastructure workload, efficient host offloading and acceleration, where compute cores are preserved for applications and not for infrastructure or data path movements. You also get low latency access to data and minimized jitter so that CPU is not stalled waiting for data from I/O or memory. Hence, an architecture that delivers right acceleration at the right place in exactly the right portion to process infrastructure workloads without stranding expensive resources. So now that we've reviewed market realities, infrastructure challenges, and emerging scale-out data center architecture for compute, let's look at the current DPU landscape. ARM is the incumbent compute when it comes to DPU, given our performance and TCO leadership. We own DPU sockets from largest hyperscalers with custom DPUs to standard merchant SKUs offered by silicon partners and startups. Some of you are present here in this venue. So we thank you for your partnership and building your products with us. Here are some examples of DPUs that are available in the market today. AWS Nitro V5, our latest DPU engine powered by ARM that delivers 60% higher packets per second, 10% lower latency, and 40% better perf per watt than prior gen. Intel Mount Evans and Marvell Octeon with latest Neoverse design IPs. And also NVIDIA and AMD with their Cortex IP and on path to the Neoverse. Now, let's shift gears to software. As you know, hardware is only as good as the breadth and depth of the software supported on the platform. Our software ecosystem is robust and rapidly growing. We engage in hundreds of open source software projects. We have hundreds of ISPs supported on the ARM platform, and we continuously optimize and upstream our contributions to open source software communities. And here's a snapshot of number of open source software projects we upstream our contributions for optimized libraries on ARM. TensorFlow and PyTorch libraries for machine learning workloads, SPDK and MySQL, optimized libraries for storage and data workloads, OpenSSL, IPsec libraries for security workloads, DPDK, VPP, VectorScan libraries for networking workloads, and Kubernetes and Kafka optimized libraries for containers. So you see, we make huge investments in open source software projects. We strongly believe in building the software ecosystem with community-based support and engagement. Another open source community I would like to draw your attention to is OPI, or Open Programmable Infrastructure Project. OPI is where OCP projects meets DPU. It's to create a common framework for DPUs to extend existing open source projects. OPI is focused on bringing a community together to accelerate the adoption of DPUs. OPI is in its early formation stage. There are several possible interaction points with OCP to explore how we collaborate and engage. For example, OCP hardware and core design project, Dash and Psi project in OCP networking, data center modular hardware systems, computational storage, open accelerator infrastructure, and composable memory system. Some of the working groups in OCP are already engaged with many of the members of OPI as we look for ways to extend the standards to support DPUs. So in closing, collaborate with us via OCP and OPI to help accelerate the adoption of DPU technologies. And thank you for listening, participating, and contributing to the OCP Regional Summit. Any questions? I know I'm between you and your beers. I'm around, so feel free to get me anytime. Okay, thank you all.
Thank you so much, Biren.